Okay, this is the last of the videos on three-phase. In this particular short video, we want to look at a different kind of connection. This figure illustrates a connection between a Y configured load and a Y configured generator and a delta configured load. I will say that what is missing here is in this particular figure, this was the best one I could find, and I didn't want to try to hand draw one. In this particular figure here, the author of this textbook has not illustrated the generator impedance or the line impedance. So I really just put this figure here so that you could see the fact that the A port of or the A terminal of the generator end is connected to the A terminal of the delta end, but then you can see the delta end has this triangular shape. So A, B, and C are connected actually to two different impedances, and this is just a different configuration. And you'll notice on the load end with this delta connection, there's not a neutral point or a neutral node. So the Y connection actually has four nodes, A, B, C, and neutral, whereas the delta connection only has three nodes, A, B, and C. And the neutral wire is a virtual wire. Now, in a balanced system, one can make the argument this doesn't matter because remember there's no current in the neutral wire and no voltage along the neutral line when the system is balanced. So from that perspective, whether or not you have an actual neutral wire connection shouldn't matter. So it just means the load is in a different configuration. In this particular case, you notice that the line currents will be not the same as the currents through the individual load legs. So IAB, which is the current through the load from node A to node B, is actually not the same as IA. And it was in the case of the delta to delta connection. But in the delta to Y connection, notice that IA splits here at node A and is shared between these two impedances. And so the line currents and the phase currents at the load end are not the same. On the other hand, at the load end, the phase voltages, which is defined as the voltage of a single phase across the load, is actually the same as the line-to-line voltages. So in a Y to delta connected load, there is no square root of 3 conversion that gives you a different line-to-line and uh, phase voltage. The voltage between the lines and the voltage of a given phase are going to be the same. In the delta connected load, the difference comes in between the currents in the line and the currents through the load, as you can see from the figure. So if we were to just isolate the load to make this a little easier to look at, for example, if we look at this particular pair of nodes, node A and B, the voltage between node A and node B, which because it's across one of the legs of the load is defined as the phase voltage, is the same as the line-to-line voltage between A and B. The currents, on the other hand, we can obtain by writing a KCL equation at the nodes. So at node A, we see that current I little a big A is basically equal to IAB minus ICA, and so on for the other two nodes. That gives us these relationships. If we then realize that the line currents are, because this is a three-phase problem and it's balanced, that they're 120 degrees out of phase, and we define a generic phase current with I phi, then a generic line current with I phi, for meaning just the magnitude of one of the line currents. Then we can see that if we have this line current IAA, that in the first phase we would have I phi angle 0. In the second phase we'd have I phi angle minus 120, so we can make that substitution and we can solve for the current in the line as a function of the current in each part of the load. So in the delta connected load, the line current is equal to the current through each phase of the load times the square root of 3 with a negative 30 degree phase. So it's a little bit different than the relationship between the voltages in the delta connected load, in that the phase is negative, and in that in this case it's the line current that's going to be the larger current when compared to the current in each phase. So these are the relationships. If you know the line currents, IAA, you could actually get the phase currents by inverting these equations. If you know the phase currents, you can get the line currents by getting these equations directly. That becomes significant because the question is, if you have a delta connected load, how do you draw a single phase equivalent and solve for that, and solve for everything you need to solve for? So before we do that, here's just a phasor diagram showing positive and negative phase sequencing, showing the relationship between line currents and phase currents for a delta connected load. Please remember this is at the load end only. At the source end, because the source is a Y-connected source, the phase currents and the line currents are going to be equal because they're basically going to be all in series. So this is referring specifically to the load and how the load is different. So how do you solve for things in a Y to delta configuration? The easiest thing to do is to convert your delta load to a Y load. And the way to do this is to take each impedance in each leg of the delta impedances and convert it to a Y impedance. And you do that by taking the amount of the impedance and dividing by 3. So if you had, for example, 3 30 ohm resistors connected in a delta configuration, and you wanted to convert that to a Y configuration, that would go to 30 over 3, or 3 10 ohm resistors connected as a Y. So it's the delta to Y conversion that many of you probably skipped or didn't really go into in depth in circuits 1. Now once you have the delta load converted to a Y load, then basically the problem becomes just like the example problem we just worked, where you can do your single phase equivalent. And when you have your single phase equivalent, you're going to want to solve for your line currents, your phase voltages, and your line to line voltages. At this point, once you have your line currents, you would convert back to a delta load. And then you have your line to line voltages from previously solving the problem, and you can use those to find the currents in the load. Or you can use those relationships we showed on the previous slide between the phase currents and the line currents to find the phase currents, since the line currents don't change with the change of configuration from Y to delta. So let me go back a couple of slides and we'll look once again at this load. So the bottom line is, if you convert this to a Y configuration, you can still solve for the line-to-line voltages between A and B. So that would just be your VAB, your line voltage. Now when you convert back to the delta, notice that you can get this IAB by just taking the voltage between A and B and dividing by Z delta. So that's probably the most straightforward way to do this, is to just find those voltages across the impedance, then convert the impedance back. This uses an important principle from circuits 1, and that's the principle of terminal pair equivalence. So what I'm really saying is, I can break this circuit right here. I can pull out this delta connection, replace it with a terminal pair equivalent, and looking in this direction, you don't know the difference. It's like this is in a black box. If I replace this with an equivalent circuit, my line currents, my voltages between the lines are going to be the same. That's the definition of terminal pair equivalence. So you can convert to Y configuration, you can convert back to delta configuration. These currents going into that black box and the voltages between the terminals coming out of the black box are going to remain the same. So the easiest thing to do, in summary, on the Y to delta configuration is to convert your delta impedance to a Y impedance, solve the problem just like we did in the previous example, and then use your phase voltages to get your phase currents.